Tantor Audio, a division of Recorded Books, presents The Next Supercontinent, Solving the Puzzle of a Future Pangea by Ross Mitchell, narrated by Derek Shoales. Preface. Who controls the past controls the future. George Orwell. This is a book about supercontinents, land masses from which today's continents are born. It explains the evidence for supercontinents' existence and the predictions of a next supercontinent, expected to form some 200 million years from now. This is also a book about how science is done. The scientific method is iterative. The next supercontinent is a scientific hypothesis, and a scientific hypothesis is nothing if it is not tested. As we cannot wait around 200 million years to see if our models turn out to be right, we must use the geologic past to test our ideas about the future. This will also necessarily be a story about scientists. A mentor of mine insists on including pictures of scientists when explaining scientific concepts as a reminder of the people behind the theories. Some scientists are willing to take their hypotheses to the grave, even in the face of dissent. As a German physicist Max Planck is often paraphrased as saying, "Science advances one funeral at a time." Others are willing to accept new evidence while they're still alive, to change their minds and to put their stamp of approval on competing ideas. As a scientist myself, I ascribe to the hopefully balanced philosophy that it's okay to like your hypothesis if you love testing it. In high school, I loved all the sciences, particularly chemistry and physics, but wasn't so much a fan of the hours of indoor laboratory experiments. When I arrived at college and heard rumors from classmates that introduction to geology blended all the sciences and required fieldwork outdoors, I was immediately sold. When I showed up to the first field trip donning a fresh pair of Carhartt pants, the centerpiece of the geologist's uniform replete with a loop for holding a rock hammer and a back pocket wide enough for a standard waterproof field book, my professor said I was destined to be a geologist. How right she was. Since that fateful day, I have never wavered from the path of learning more about Earth. I went on to earn my PhD in geology and geophysics at Yale University, did my postdoc at Caltech, was a research fellow in Australia, and am now a professor in Beijing, China, at the Institute of Geology and Geophysics, Chinese Academy of Sciences. Studying the drift of the continents over billions of years, I have conducted fieldwork on every continent except Africa. Rocks scattered around the globe are sample sites targeted for solving the next big problem. Time in the field collecting rock samples makes for time back in the laboratory, making careful measurements. But the majority of my time is spent reading, thinking, and writing, and thinking some more. Why we call it research. My goal is to integrate plate tectonic theory with an understanding of the whole planet, whereas now it is largely a description of the motions of plates at Earth's surface. To do so, I make an effort to expand my own thinking, to address the work done by other geologists that study rocks formed at greater depths of the planet, and that are subsequently exhumed to the surface, as well as the work of geophysicists and geochemists investigating Earth's rocky mantle and its molten core. You may also come away from this book with a better understanding of geology. Geoliteracy, to borrow and bastardize the term from National Geographic, is more important than ever. Although their use of the term focuses on geography, even geography changes as the world changes over time, with once wet climates becoming dry, which is partially why our natural resource needs are shifting toward renewable sources. We need to augment geography, the study of our planet, its atmosphere, and human activity, with geology, the study of our planet's entire physical structure. Climate change is our new reality. I believe one reason for the apparent gap in public and political, if not scientific, opinion on the matter of global warming is the lack of understanding. Geology was only an elective in school when I grew up. How can we have a meaningful discussion about climate when many have so little basic knowledge about how Earth works? Humanity's evolution is now understood to have a close relationship to plate tectonics and climate change. Although the tectonically carved deep lakes of the East African Rift provided a cradle for some of our earliest civilizations, when these lakes dried up due to earlier climate shifts, Our ancestors' entire way of life needed to change. They needed to walk distances previously unimaginable to find habitable land. The polar ice caps that our species have always taken for granted in Antarctica and Greenland are melting at an unprecedented rate. The increasing atmospheric concentration of greenhouse gases begets global warming, which begets ice melting, which begets higher sea levels, warmer oceans, and a climate never experienced by our species. Understanding how today's global climate change will affect our way of life, therefore starts with understanding the plate tectonics that underlies why, for example, we have polar ice caps in the first place. Until humans came on the scene, plate tectonics predominantly controlled the concentration of greenhouse gases in the atmosphere through volcanic emissions. This volcanism is in turn due to the motion of Earth's tectonic plates. Understanding how plate tectonics have caused swings between greenhouse and icehouse climates in the past is therefore critical to understanding what our own emissions might be capable of, as well as how we may be able to mitigate warming. This brings me to my ultimate goal for the book: to bring you up to date on the current state of knowledge of plate tectonics. The large-scale appearance of our Earth's surface will change very little over our lifetimes, but over the billions of years of geologic time, these changes have been immense. I hope this book will provide you with a better recognition of what this geological force has created, from the 9,000 meters high of Mount Everest to the 11,000 meters low of the Marianas Trench. And it hopes to offer a better appreciation of how landmasses, now thousands of kilometers away from each other, can merge to form the next supercontinent, when the majority of Earth's continents will come together to form a large, long-lived landmass. If our species lives to see the next supercontinent, then we will have achieved what no other mammal has ever done: survive more than a few millions of years. Our oldest immediate ancestors, the primate species of the genus Australopithecus, lived only about 1 million years. The longest living mammalian species have existed only since we mammals filled the niches vacated by the extinction of the dinosaurs 66 million years ago. If current theories about the extinction of the dinosaurs are correct, then our current dominance may well be a cosmic accident. Species larger than bacteria that have survived for hundreds of millions of years are hard to find. Thus, the task ahead, our survival as a species, is unprecedented. And while such longevity may seem far-fetched, doesn't it also sound a lot like us? Look at our list of achievements: domesticating fire, cooking, creating languages, inventing the wheel, discovering mathematics, controlling electricity, exploring space. The survival of our species long enough to see a new supercontinent take shape means we will also need to overcome the human-induced environmental challenges of climate change. The forces of plate tectonics and of human-induced warming of the planet are comparable. Many argue we are now in the Anthropocene, a period in Earth's evolution defined by human intervention. Geologist turned climate scientist Bob Kopp was one of the first to point out that humans have become a geological force to rival plate tectonics. Human-caused carbon dioxide emissions, for example, now match those from the world's volcanoes. And many of our geoengineering solutions for reversing climate change, such as releasing sulfur into the air to cool the planet, or carbon capture by growing and burying trees, involve, as we will see, humans behaving the way plate tectonics does. Tectonics is the most fundamental control of climate change, and so it is no understatement to say that to solve climate change means nothing less than adopting a mindset of tectonic proportions. Understanding what the next supercontinent may look like is surely speculative, as it will not happen in our lifetimes or those of our children, grandchildren, great-grandchildren, or their even more distant descendants. Still, I hope this book will encourage you to reflect and speculate on the changing shape of our planet, and on the importance of looking at our planet's evolution at a time scale much longer than that of individual human existence. Introduction. In grade school, many of us learned how the present continents scattered around the globe once fit snugly together. Although each continent appears to have its own particular shape, rewind the tape 200 million years, and they fit together, like the pieces of a jigsaw puzzle. Pangea, coined by plate tectonic pioneer Alfred Wegener, means just that. All Earth. A time in Earth's past when the majority of the continents assembled into a single plate. But Pangea is just the most recent iteration of what's called a supercontinent. At least 2 others have come and gone over the 4.5 billion years of our planet's existence, and scientists like me believe there will be more in the future. The next supercontinent will likely take another 200 million years to form, but the continents are undeniably on a collision course. According to one computer model, New York City will crash into Lima, Peru. Plate tectonics is certainly powerful enough to stack one city on top of the other, sending the future's equivalent of skyscrapers into the depths of the ocean to be recycled back down into the hot mantle. Although scientists agree that another supercontinent is coming, we have vastly different opinions on how it will take shape. In this book, I will lay out the leading contenders for the geography of the next supercontinent, explore the modern mysteries that still surround plate tectonics, and explain the science behind predicting how continents move. Alas, predicting the next supercontinent is not as simple as understanding today's movements and pressing fast forward. Tectonic plates move slowly, at about the same speed that our fingernails grow. But GPS is now precise enough to detect this slow motion, and residents of Pompeii, San Francisco, and Fukushima can tell you that the effects of those movements are hard to perceive, until they are devastating. Volcanoes, earthquakes, and tsunamis are evidence of plate tectonic's power. So is geography. Just look at the abrupt bend or kink in the chain of the Hawaiian Islands. These islands formed a straight chain of semi-continuous volcanic activity for about 30 million years, until a sudden pivot occurred over the course of a few million years or less. The bend is a record of that pivot. Why did this happen? The tectonic plates are all interconnected, so any change in the movement of one plate causes adjustments in them all. 30 million years ago, Australia broke away from Antarctica and started its current path north across the Pacific Ocean. Whereas the Pacific plate had been moving directly north before the bend, Australia's breakaway in the western Pacific caused the motion of the Pacific plate to deflect toward the northwest after the bend. No plate is moving alone, and each plate interacts with its neighbors along their shared boundaries. Plate tectonics is the dance of all plates, and the 7 major continents, or 8 depending on how you define them, they carry, constituting a global choreography with dozens of smaller plates in between. The earliest understanding of plate movement was the 16th century idea of continental drift, that the continents migrated like rafts slowly into their current position, floating on an imperceptible layer within the Earth. But this theory was largely written off because it was not clear what sort of mysterious substratum the continental rafts would be floating on. By the beginning of the last century, we still knew very little about the interior of the Earth. Eventually, as seismology, the study of inner Earth using the vibrations generated from earthquakes, developed, and submarines were put to good use after World War II to map the seafloor, the hypothesis of plate tectonics changed geology forever, breaking Earth's seemingly rigid surface into an interlocking mosaic of different plates that pushed and pulled each other, provided a unified explanation for the origin of many of Earth's great geological features, such as mountains, volcanoes, earthquakes, and oceans. But as exciting as the early plate tectonic revolution was, it didn't have all the answers. For example, the hot interior of the Earth was like a convecting in a movement driven by temperature changes, just like the circulation of air in the atmosphere. But how these deep convective cells related to the push and pull of the plates at Earth's surface would remain elusive for decades, and the details of this interaction are still unsolved. Beneath all the plates, the thickest layer of the planet, the solid but pliable mantle, plays a major role in plate tectonics. Without getting into details of specific hypotheses discussed later, the basic processes of plate tectonics according to the current state of knowledge explain plate boundaries, continental drift, opening and closing ocean basins, and planetary cooling through mantle convection. Simply stated, the moving plates are the surface manifestation of mantle convection, and all these processes are linked. Where plates converge, one is thrust beneath the other and sinks back into the interior of the Earth. This interaction often occurs where convection in the mantle has a cold downdraft, where plates are pulling apart, as in the East Africa Rift Valley today, which is often where convection in the mantle is upwelling as a hot plume. When on Earth did plate tectonics begin? Have we always had it? Although we take the modern plate tectonic network for granted today, there is mounting evidence that Earth did not always have plate tectonics, and that Earth's tectonic style has evolved over time. Indeed, there is fragmentary evidence for plate tectonic-like processes potentially happening in a very primitive Earth. However, much of this evidence from our most ancient rocks assumes their geochemistry is similar to that of modern rocks, and so is interpreted in terms of plate tectonics. But such similarities can also have alternative explanations. If Earth didn't have plate tectonics in its infancy, then how did our young planet behave, and how did it evolve in such a way that plate tectonics developed? Putting plate tectonics into the broader context of Earth's long history makes us realize that the current presence of plate tectonics is no guarantee that it will continue forever. Why? Earth's internal heat budget, the fuel on which our plate tectonics engine runs, is a finite energy source. It is therefore impossible that plate tectonics will operate indefinitely. Maybe a future Earth will look more like the scorched, stagnant lid of tectonically inactive Venus. But rest assured that plate tectonics will last long enough to form another supercontinent, and most likely even a few more cycles after that. But in this book, we won't speculate beyond the next supercontinent just ahead of us. A 200 million year forecast is sufficiently speculative. While on the issue of prudence in forecasting the future, I should make a note about the scientific approach taken in this book, as well as the science that's in it. Predicting the next supercontinent is fertile ground for wild speculation. Scientists have given numerous interviews describing their speculations about the nature of the next supercontinent. Indeed, often reasonable rationales are provided to bolster these opinions, but these public speculations haven't faced the scrutiny of scientific peer review. With the exception of the book's philosophical last chapter on human survival, we will deal mostly with hard-fought, peer-reviewed scientific papers as evidence or theory providing the basis for our arguments. The scientific literature will be our check. It's all but inevitable that another supercontinent will form, and some obvious signs, the megacontinent of Eurasia is nearly halfway there already, even show that the process is well underway. No, we cannot test our hypotheses for the next supercontinent by waiting around to see what happens. But because Earth has seen multiple supercontinents in its past, we can use the lessons learned from these previous cycles to test our models for the future. Geology first became a serious science by sticking to its founding adage, a principle called uniformitarianism, that the present is the key to the past. But now, as practitioners of a scientific field 2 centuries old, geologists have learned a great deal about the natural experiments that have played out through Earth's 4.5 billion year history. We now believe that the context of the past is the key to understanding the snapshot of the present and to project into the future. Geologic history repeats and will continue to do so. In order for another supercontinent to form, entire oceans must cease to exist, and predicting which oceans will disappear or close, and why, is a lively debate among geologists. When I was a graduate student, traditional models for the next supercontinent called for closure of either the Pacific or the Atlantic Ocean. Since the Pacific Ocean surrounded, that is, was external to, the last supercontinent, Pangea, and the Atlantic Ocean is the internal ocean that opened up during the breakup of Pangea. These previous models of the supercontinent cycle were dubbed extroversion, for closure of the Pacific, and introversion, for closure of the Atlantic, respectively. There are still stalwarts of introversion and extroversion, and certainly no consensus yet as to which of these models applies to the next supercontinent. Nonetheless, rejuvenated interest in supercontinent formation is driving new research, and any refined understanding of plate tectonics writ large will be a vast improvement on today's textbooks. In this book, we will discuss several possibilities for future supercontinents. I will also explain why I place my bets on Amasia, a supercontinent predicted to form at the North Pole. Instead of either the Pacific or the Atlantic Ocean closing, I think evidence points to something more complicated. Close the Caribbean Sea, and the Americas will fuse together. Close the Arctic Sea, and the Americas will fuse with Eurasia. The model predicting Amasia is the first to consider the controlling effect of Earth's mantle, the massively thick layer of the planet between the core and the crust, and its massive and forceful convection currents. Even if I fail to convince you that Earth will next host Amasia, this book will leave you with a better understanding of supercontinents and the science behind the very ground beneath our feet. Chapter 1. Pangea. The resistance to a new idea increases by the square of its importance. Bertrand Russell. The last time the continents were all connected as one landmass, the dinosaurs still roamed the Earth. But when supercontinent Pangea first took shape about 320 million years ago, even these dinosaurs were still twinkles in their evolutionary ancestors' eyes. It was only shortly before Pangea's formation that animals first climbed onto land from the sea. By the time the continents came together, the first amphibians had spread all over the world. At the same time, in the Carboniferous period some 300 million years ago, oxygen rose to its highest levels ever, about 30% atmospheric concentration, whereas today it is only about 22%, allowing newly evolved insects to grow so big that dragonflies were the size of watermelons. Elevated oxygen gave rise to the largest animal vertebrates ever, those dinosaurs who enjoyed their heyday during the peak of Pangea, even after oxygen levels dropped precipitously. Pangea is the most famous, most recent, and most studied supercontinent. And surely most everything we know about more ancient supercontinents uses what we know about Pangea. And yet, we still don't know everything about Pangea. Why it came together and why it broke apart are the most critical pieces of information for answering the question of what the next supercontinent will look like. We arguably now know with incredible precision what continents were included in Pangea, where they were positioned, and when they assumed this configuration. But why Pangea took its particular shape, and ultimately how it assembled, is still unknown. When I was a graduate student, I read geologist Brendan Murphy and Damian Nance's paper, The Pangea Conundrum, and was fascinated. Murphy and Nance were identifying a systemic problem surrounding supercontinent research and bringing to light a scientific crisis. I realized they were calling for nothing less than a paradigm shift in supercontinent research. So, what was the crisis? Murphy and Nance discovered that the observations didn't match the calculations. Between 600 and 400 million years ago, during the dawn of what's called the Pangea Assembly, there were two ocean basins, the vast and old Paleo-Pacific Ocean external to the continents, much like today, and a series of smaller and young oceans, the Iapetus and the Rheic Oceans, that opened at this time and were internal to the continents, like the modern Atlantic Ocean. Theoretical expectations suggested that oceans of old, cold, and dense crust were most likely to vanish by sinking into the mantle. This expectation was further supported by the fact that the young and internal oceans at that time were pushing the continents away from the hot mantle upwelling over which they had opened, causing the continents to drift downhill, where cold mantle was already downwelling due to convective sinking. Put another way, the continents should have formed together over the Paleo-Pacific, and the Iapetus and Rheic Ocean should have expanded. But the accepted shape of Pangea is the opposite. Goodbye Iapetus and Rheic, long live the Paleo-Pacific. Murphy and Nance's conundrum, then, was how to explain why the assembly of Pangea was accomplished by continents consuming their young, hot, buoyant internal oceans only shortly after they were created. why did the motion of the continents quickly reverse itself instead of continuing and consuming the older, colder, denser external ocean? Did something in the mantle change? Which of the assumptions was flawed? One of the first things students of plate tectonics learn is to draw a force diagram of the system, depicting the pushes and pulls on the plates. Some of the forces come from the plates themselves. Slab pull, where a sinking slab pulls the plate down into the mantle, or ridge push, where the creation of new ocean crust at the surface pushes the plate away from this spreading ridge. Some of the forces even come from the mantle below the plates. Even though the rocky mantle is stiff because it is under immense pressure, due to lying deeper in the earth than the crust, it is actually slowly flowing like a very thick syrup because it is so hot close to the core. As a result, the mantle convects, acting like the air in your oven, in which hot air rises as cold air sinks and displaces it. Convective flow in the mantle tends to drag the motion of the overlying plates along, in addition to pushing and pulling forces acting on the plates themselves. How these different forces combine determines which direction a plate moves and how quickly. Of the forces within the plates themselves, it is slab pull that is thought to be the strongest. Slab pull is in fact so much stronger than ridge push that the former is often referred to as active and the latter as passive. Ocean crust first forms at an ocean ridge where the hot mantle upwells to the surface. As new mantle upwells and pushes away yesterday's crust, that old ocean crust cools, contracts, and becomes denser. The older and denser the ocean crust, therefore, the more likely it is to sink back into the mantle and vanish, allowing continents to collide. And the forces of the plates can often work in tandem with those of the underlying mantle convection. If you look at where slabs are getting pulled down into the mantle today, it is also where the mantle itself is downwelling due to cold material sinking by convection. In other words, slabs are pulling and the mantle is dragging the continental plates to largely the same places. But when Murphy and Nance applied these principles to Pangea, they couldn't get it to assemble the way we know it did. The duo were experts on which oceans closed in order to assemble Pangea. The Iapetus and the Rheic, oceans that had once separated North America and Europe from the southern continents of Pangea, known as Gondwana. The only problem was that this separation had occurred only some 550 to 450 million years ago, making the Iapetus and Rheic oceans likely the youngest, most buoyant oceans around when they vanished shortly thereafter, between 400 and 300 million years ago. To make matters even more confusing, evidence shows that the larger and older Paleo-Pacific Ocean, external to the continents, had started to vanish, as expected. But instead of these sinking slabs pulling the continents outward to consume the Paleo-Pacific, the continents collapsed inward, consuming their own internal oceans. As specialized as scientists must become, there is unfortunately quite the divide between those calculating the forces to explain plate motions and those that detect the evidence showing how the motions took place. One of my graduate school advisors, Mark Brandon at Yale University, taught me to regard science as a crossword puzzle. In a crossword, there are words that go vertically, downs, and those that go horizontally, acrosses. For these two types of words to intersect and for the puzzle to be solved, there needs to be an internal consistency between acrosses and downs. By analogy to scientific expertise, there are those who specialize in downs and others that specialize in acrosses. In the case of supercontinents, expert computer modelers who can calculate the myriad forces pushing, pulling, and dragging the plates, geodynamicists, specialize in acrosses. And those that specialize in downs are the rock experts who can tell the story of which continents collided and when, geologists. Essentially, the reason behind this scientific crisis, Murphy and Nance correctly assumed, wasn't that the geodynamicists or the geologists were wrong. It was that they needed to take into account each other's constraints. Murphy and Nance's contribution was getting these two groups of experts to admit that they were trying to solve the same puzzle of Pangea assembly, and that they needed to work together.
Sample complete. Ready to continue?